So, now what we really understood was we need to do many tests on the bitumen. In fact, if you see the recap quickly related with the viscosity grading, in viscosity grading we measured penetration at 25 degree centigrade, softening point, viscosity at 60 degree centigrade and kinematic viscosity at 135 degree centigrade. Viscosity at 60 degree centigrade was performed by you using a vacuum capillary viscometer. You subjected the sample to short term aging and a ductility test was carried out, as well as penetration was carried out, and then the viscosity at 60 was measured, and all of them were measured at a fixed temperature, and depending on the grade values were given here. Now, let us take a look at what we discussed till now for the PG. First and foremost thing is, as far as the construction operation is concerned, we are still going to do the test at 135 degree centigrade, but instead of using a kinematic viscometer, we are going to use a rotational viscometer and record the absolute value of the viscosity, that is number 1. Then after that, for rutting we are going to measure the rheological properties at unaged and short term aged conditions depending on the geographical locations where you are going to construct. And in fact, if you notice it, these values 1 kilopascal or 2.2 kilopascals were fixed, and you are expected to find out the temperature at which these values will be met. Then after subjecting the sample to short term aging, we also subject it to long term aging. And we are going to do it for fatigue, and then for low temperature we are going to do a BBR or a direct tension. So, there is going to be RTFO aged sample, there is going to be an RTFO plus PAV aged sample. So, looks like we have a complex set of testing that needs to be done. Not only that, we also need to spend some time thinking about the maximum intermediate temperature as well as the minimum pavement temperature where you are going to construct a road. When we talked about viscosity grading, I gave you an indication about which grade should be used depending on the geographical location, but here it is lot more specific. Okay, right. So, I am just going to read out few sentences from the ASTM D 6373 binder specification, and the most important is the grading designations are related to the average 7-day maximum pavement design temperature and minimum pavement design temperature. In the earlier version there was only one table that was given, but in the recent version of ASTM D 6373 two tables are given. There is a procedure that is given as using 6816 in table 2, and that tells you how to find out the critical low cracking temperature using a combination of test methods, but if we will be discussing it as we go along. But if there is no table that is specified, a SuperPave says you just take table 1. This is more or less similar to the ASTM D 3381, in which there was two table that was mentioned, in which the default was taken as table 2, if you recollect the discussion we had, right. Now, this is the crux, this is the table that you need to see here very carefully. So, I have split the specification into two portions here. What you see here is performance grade PG, and it is 46 or 52, and the table is quite long. It will be given to you as part of the course material, so you can take a look at it. So, this says average 7-day maximum pavement design temperature should be less, if it is less than or equal to 52 degree centigrade, you take a PG of 52. Okay. So, what you should do is to get some idea about the expected air temperature for the next 10 years, use some kind of an algorithm to find out what will be the pavement temperature, and knowing the pavement temperature, find out what is the average 7-day maximum pavement design temperature, and if it is less than, for instance, if it is less than 52, then you take a PG 52. Now, you will also notice that there are some values that are given here minus 10, minus 16, minus 22, minus 28, minus 34, minus 40 and minus 46. These are the minimum pavement design temperature. So, that means if you write Pg 52 minus 10, so this corresponds to this value. So, this particular grade of bitumen can give a satisfactory performance if the 7-day maximum pavement design temperature is less than 52 and it is up to minus 10 degree centigrade. Okay. Now, for this particular location, ASTM prescribes that you should do the PAV aging temperature at 90 degree centigrade, and you also see that there is a intermediate temperature that is prescribed here. So, this is for the fatigue part. So, after doing the short term aging and when you do the long term aging at 90 degree centigrade, and when you measure the G star sin delta values here, you are expected to, if the value that you measure is around maximum of 5000 kilopascal when you hit it at 25 degree centigrade. So, that for any temperature above 25 degree centigrade it is fine, but if it is going to be below 25 degree centigrade you are going to have a problem with this. So, this is the limiting value that is given here. So, how do we get this 56, 10 and 25? In fact, if you actually take a look at it, it is a very empirical algorithm that is used. So, 52 and 10, so the difference is going to be 62, right, and 62 divided by 2 is 31. So, if you take 52 minus 31, you are going to get 21 and they add 4 degree centigrade here to get this 25. Okay. So, that is the way in which these things are computed. The reason why they are computed like this depends on a detailed weather analysis as well as the use of the master curve also. For instance, any binder that passes G star sin delta at less than 52 degree centigrade should also show a G star times sin delta of a maximum of 5000 kilopascal at a 25 degree centigrade, less than 25 degree centigrade. So, this is understood. Okay. So, you have to notice few other things. There is a 6 degree difference between each PG 46 and 52. Originally it was 3 degree centigrade, but when the binder manufacturers expressed objection, it was cut short it into 6 degree centigrade. You will also notice that there is another 6 degree difference in the lower temperature, but when you look at the intermediate temperature, the same 3 degree centigrade is maintained here. Okay. So, to summarize, this is a very important table. To summarize, you have to find out the air temperature, you have to find out the pavement temperature. Knowing the pavement temperature, compute the average 7-day maximum pavement temperature, right, and then check for what is the PG that you will use. Now, if you know what is the PG that you are going to use, you will be able to prescribe limits for rutting as well as fatigue, and the minimum pavement design temperature will also be given by the depending on the weather conditions, and then the temperature at which you have to age your binder to simulate the long term aging is also prescribed by this. And in fact, what you see here is temperature plays a very critical role in PG. Unlike viscosity grading, in which we did not worry about anything associated with temperature, we just measured one at 60, one at 20 degree centigrade and a softening point temperature, and we just moved on. But here you are worried about all these temperatures, and you also need to understand that from G star by sin delta at rutting, which is at high temperature, to the appropriate value of G star times sin delta for the fatigue, you have to understand that these numbers have been worked out based on the manner in which the master curve of the material exhibits its behavior. Okay, right. So, what is the reason for this? So, this G star by sin delta of value that is given here as 1 kilopascal and 2.2 kilopascal is related to the early part of the payment service life. And how it is written here, please understand this carefully, look at this. Here in performance grade specification, the spec parameters come to the left hand side and the temperature is listed in the main table. So, it says G star by sin delta minimum 1 kilopascal remains the same. That is the most important thing, whether you construct the road in Chennai or in Nagpur or in Srinagar, the parameters related to rutting remain the same, only the associated temperature changes. That is not the same case when we did the viscosity grading, in which we kept the temperature constant and we only varied the viscosity, but here we are keeping the rutting parameter constant and we are only looking at the variation associated with the temperature. So, in fact, this is a very interesting graph, you will see it in the FHWA report that I referenced in the earlier. You can actually see how one got this 1 kilopascal. Lot of data was collected, and in fact, what you see here is only a snapshot. So, they were trying to see whether the rutting rate versus G stars by sin delta can have some relation. So, when they extended this, it came somewhere below 1 kilopascal and they kept it as 1 kilopascal for the rutting requirement. And there is always an idea that when the material ages, the viscosity of the material for most of the binders, if it is a good performing material which is not having a very high aging susceptibility, the viscosity increase will be in the order of 2 to 2.5. For reasons best known to them, they took it as 2.2. So, that is why you also get that as 2.2, right. So, as far as the fatigue is concerned, one needs to understand this very carefully. Always the terminology of fatigue cracking is used when it is specified, because in the field what you see here is something like this, your map cracking or alligator cracking. But when we do the test in the laboratory, we never crack the sample. The bituminous binder is subjected to only a testing at the particular intermediate temperature. So, what we are doing is we are actually making a jump here, finding out what is the damage or the energy that is dissipated in the material during that particular temperature, and then making a connection with what can happen if that binder is used and how it can lead to cracking at the intermediate temperature. So, again lot of statistical analysis, field data, laboratory data have been used before this parameter has been worked out. In fact, and this is more or less at the later part of the payment service life. So, that is why we do the RTFO plus PAV aged material here, okay, right. And in fact, if you look at it from the fatigue damage perspective, the specification requirement to address fatigue cracking is kept at 5000 kilopascal. And if you actually see the old graph, I could not get a better graph than this. In the olden days, they used to believe only in 3 megapascal. Okay. So, this is the estimated G star at 10 radians per second. So, this is what was carried out on the percentage fatigue cracking. Basically, you see a very good functioning pavement, a test track, try and collect, find out what is the cracking intensity that has happened there, try to collect the binder from there and do a testing, and then try and see whether you could come out with parameters that could be related with the fatigue that you are seeing there. So, this was taken as the suggested 3 megapascal limit for controlling the age hardening as well as fatigue, but later it was moved into 5 MPa. Okay, right. So, how do we do this, go about doing this? So, we need to get lot of air temperature data, and in fact, what is given here as SHRP A648A has that. Then you also have various SHRP reports of 367, 368, 369, 370, more or less list how this performance grade specifications came out. You can actually go search for A367, you will be able to get these details. Okay, right. How do we finally choose a PG grade? If you know the geographical area, you can choose it. If you know the pavement temperature, you can choose it. or by means of an air temperature. If you do not have any access to any of the algorithms that are used, there are PG maps are given in which you can look at your district and then find out what is the PG that is needed. But if you have the pavement temperature data with you, well and good, you can choose the PG, or if you say no, I do not have the pavement temperature data, I have the air temperature data, then I could calculate the pavement temperature data from the air temperature and then I could do it. Of course, whatever I am discussing is valid mostly for the North American and the European condition. We have not come to a stage in India in which we can actually show this kind of weather map. So, how do we really compute the hottest pavement temperature? We need at least weather data for 20 years and we calculate the average maximum air temperature for a 7-day period, and then we calculate the 1-day minimum air temperature for each year. So, this is the empirical expression that was given by FSWA. You can actually see that T20 mm is the high pavement design temperature at a depth of 20 mm. This is the air temperature, this is the latitude. We have a similar expression that we developed at IIT Madras for Indian conditions. The details have already been explained in few other lectures, and this is the minimum air temperature. It is the given, this is the minimum air temperature and this is the minimum pavement temperature, right. So, now when we are going to get into all these things, we also need to understand that weather prediction is always subjected to its associated variability. So, one cannot really design on a PG grade without understanding what is really called as the reliability. So, what exactly is defined as the reliability, and this is something well known to all of us, but I will just state this: percentage probability in a single year that the actual temperature either 1-day low or 7-day high will not exceed the design temperature. So, if I am going to use a 90% or 95% reliability, then I am really talking about the lower risk here. So, how do we do it? So, if you typically assume that the data is normally distributed, so you are talking about picking something as the design temperature on either side. In fact, what we will do for higher temperature, we will go to this side, and for lower temperature we will be going to the other side. I am going to illustrate it with a very simple example, and in fact, this example is found in the Asphalt Institute Superpave manual. So, let us take one particular case of we have mean 7-day maximum air temperature as 32 degree centigrade and the standard deviation is, so this is mu, this is sigma 2 degree centigrade. So, what this basically means that there is a 50% chance that the 7-day maximum air temperature will exceed this 32 degree centigrade. So, if I assume normal distribution, and then what I am going to do is, so 36 degree centigrade, so that means 36 mu plus 2 sigma will give me a 2% that the 7-day maximum temperature will exceed 36. So, I am looking at a 98%. Okay. So, 32 is the air temperature, standard deviation is 2 degree centigrade. So, 36 is the 98% reliability that I am going to give. So, design air temperature of 36 degree centigrade will give me the 98% reliability. So, similarly, what we do is we take the minimum air temperature is minus 21 degree centigrade and the standard deviation is 4 degree centigrade. So, 2 into 4 8, 21 plus 8 29. So, it is going to be minus 29 here and plus 36 here. Of course, since this is high temperature, we go in this direction and not in this direction, and for low temperature we go in this direction, and we normally see that there is more variation one sees in the low temperature when it comes to the 7-day average high temperature, and it is more or less the same. Once you know what is the air temperature and knowing the latitude of a specific location and using the empirical expression that was given earlier, you can actually find out what is the pavement temperature. So, if you know, for instance, if this was 32 and minus 21. So, if you use 32 degree centigrade or 36 degree centigrade and knowing the latitude, and if you use that expression, you might get 56 degree centigrade as well as minus 23 degree centigrade or 52 degree centigrade and minus 16 degree centigrade. So, if you use 52 to minus 16, the reliability here is only 50%, but if you use 56 and minus 23, the reliability is now going to be 98% reliability, you are going to get that. Okay. So, now the interesting part is, if you remember the table that I showed you, there is not going to be anything given as 56 in the table, because the next one that you are going to see is only 58 degree centigrade. So, the actual PG that you are going to see will be 58 minus 28 or 52 minus 16. So, the actual PG grade that you will be using is 58 to minus 28. So, since you are trying to fit it to the PG table, the reliability that you are going to see here in this specific case is going to be little higher than what we actually calculated here. I hope it is very clear. Now, the interesting part about the PG grading is, in fact, we will discuss these assumptions associated with G star by sin delta in a separate lecture. All these were calibrated for a 90 kilometer truck speed, okay. And there were some issues related to converting this 90 kilometer per hour to the angular velocity. So, they took it as 10 radians per second, and in fact, FHWA describes in detail some of the small errors that have crept into the specification formulation. So, what will really happen, for instance, if instead of 90 kilometer per hour, if the speed of the representative truck in that location is going to be 40 kilometer per hour, what will really happen? Since all these calibrations of 1 kilopascal or 2.2 kilopascal or 5000 kilopascal are based on this particular speed, and since we know already that as the frequency varies, changes, the viscoelastic properties also changes. So, we should be able to do some corrections here. So, this basically is given a name of what is really called as grade bumping. So, if you are going to have 90 kilometer 40 kilometer per hour in your highway, what you are going to do is, you are going to increase this by one high temperature grade, and if you are going to, let us say, build a yard in which most of the vehicles are going to be stationary, you are going to have a 2 high temperature grade. So, that means if you got something like 58 degree centigrade, and if it is going to be slow moving traffic, we move it to 64 degree centigrade. What is the tacit assumption that we have made here when we bumped the grade to 64 degree centigrade? We more or less assumed that the PG properties, the G star by sin delta, will also hold good as the speed reduces. So, in essence, you are invoking equivalence of time and temperature as you increase the temperature and reduce the frequency. It may work, it may not necessarily work, and in fact, grade bumping has never worked for modified binders, and that is why we started using multiple stress creep and recovery, which was discussed already, right. So, if you are talking about, for instance, if you are talking about a toll road where it is 64 minus 22, if it is going to be a slow moving traffic, you increase it by 1 grade 70, and if it is going to be a way station, it is going to be 76. You will also notice that nothing has actually changed in the low temperature, right. What about the traffic amount? Because the original grading that was carried out was typically for 10 million standard axles, okay. So, I will we will explain in a nutshell what exactly is the standard axle. Later when we have a course on advanced pavement analysis and design, these issues will be discussed threadbare. But if it varies from 10 to 30 million standard axles, we have to increase it by 1 high temperature grade, and if it is more than that, we recommend increase it 1 more. So, that is what we are really going to do it. And what exactly is this easel? easel is nothing but equivalent single axle load. So, what is this easel? So, this is your 80 kilonewton. So, you have a single axle with 2 wheels on either side 20, 20, 20, 20. So, if and you can actually see there is another axle that is shown here which is 100 kilonewton, another axle that is shown here which is 44 kilonewton. The concept of this easel essentially tells you that one application of 80 kilonewton is equivalent to 2.2 application of 100 kilonewton as well as the damage is concerned. Now, it is not very clear whether the damage is in terms of rutting or fatigue, because the damage will be completely different when you are talking about rutting as far as fatigue is concerned. But right now, as far as this particular topic is concerned, we will assume that both are the same. So, this is the concept that is used, and now normally what we do is, if you have a very small truck, this is how you will be computing the easel. So, for a 27 kilonewton axle will correspond to 0.01 and a 67 will correspond to 0.48. So, when you add them, you are going to get 0.49, and similarly this is for a big truck, you get 2.39. So, what you do is, wherever you are going to construct your pavement, you have to find out for your design period what is the axle load in terms of the standard axle, and then find out whether for that particular design period, if it will exceed it will be between 10 to 30 million standard axles or it will exceed, and appropriately we have to also increase the grade of it. So, finally, how to use this specifications, we need to find out the 7-day maximum pavement temperature, we need to find out the 1-day minimum pavement temperature, and then we have to use the specification tables to select the test temperatures, and basically then we have to find out the bituminous binder properties and compare it with the specification limits. So, this is the whole crux of it. Now, if we want to use PG for India, how do you think we should proceed? What are all the things that we need to understand? So, first and foremost thing is, we need the data related to temperature, and what we are talking about? We are talking about pavement temperature. So, that means we need to have test roads with sensors have to be used to collect 24/7 pavement temperature data, and we need to establish air temperature to pavement temperature correlation. Without that we cannot really proceed, because most of these correlations that are available as part of the AASHTO or SuperPave more or less correspond to what is available for North American condition. The next thing that we need to do is to have understanding of speed, axle load data, we need it for all year round. In fact, most of the time what we see here is, before a new pavement is constructed or a rehabilitation is carried out for a old pavement, we only collect 24/7 data and we do not actually have the complete data. So, we need to have full data, and only then we can actually find out what is the representative speed and what is the axle load spectrum, because when we know the axle load spectrum, we will know what kind of corrections has to be done, and when we know the speed, we will also know what exactly needs to be done here. Then we also need to find out the variability in the binder properties. So, roughly we have around, out of the 23 refineries in the country, we have 12 refineries which produce bitumen, and each of them use different process. So, we do not really know what exactly is the variability that one can expect in this. So, this is something that we need to do, and later lab, that is binder to field which is the mixture, correlations have to be worked out afresh. It is not very clear whether the G star by sin delta of 2.2 kilopascal will indeed work for the Indian condition. So, this also need to be understood, and finally, we also need to spend some time looking at the reliability data and what kind of risk that we are trying to take when we design a pavement. So, these are some of the issues that we need to keep in mind. In the next lecture, we will talk about the theoretical basis of G star times sin delta, G star by sin delta, the testing conditions, as well as how to find out the low temperature pavement performance grade. Thank you very much.